some of you may recall this topic we had started earlier also, but with some change in plan we discontinue. And so I hope some of you recall. So we had 1 or 2 sessions on waves. So I'm going to go little faster on some of the initial part of this topic, and with the hope that most of you will have some memory of what we had done last time. And to understand waves, waves also is based on SHM motion. The first thing, every time I keep repeating, understanding of phasor is important in my understanding. And what is phasor? Let's try and understand. So basically, SHM motion happens along a line, kind of linear SHM motion, but it can be treated as equivalent to a uniform circular motion, projection of a uniform circular motion. Because in certain ways, understanding a uniform circular motion is easier compared to understanding SHM motion. And we use something like phase. And that is something, and when you have uniform circular motion, just assume that there's a particle here which is undergoing uniform circular motion, and the radius of this circle is taken as amplitude of SHM, and angular velocity we always take with reference to x-axis. This is normal convention, but we can use some other convention also. Angular velocity is omega, which is same as angular frequency of SHM oscillation. So what are you going to do here? Again, this is to understand from we use a reference circle to understand phase angle. Because once we understand phase angle, from phase angle, we can find out displacement, velocity, and acceleration. That's what we're going to do. And how is the phase angle measured? Phase angle is measured with reference to x-axis in anti-clockwise direction, 0 to 360, or you can express minus angle also. So when this is here, we are going to do, we can take projection on any diameter. If we take this projection on any diameter, it will be SHM. But when we take phasor convention, we take its projection on diameter which is along y-axis, or is y coordinate of the particle which is undergoing SHM. So when it is here, if you mark its position on the y-axis, so this is the corresponding position. When it here it has moved by the angular displacement of 30 degree. When it has angular displacement of 30 degree, its y coordinate will become a by 2. Its projection on its diameter or its projection on y-axis is here. So this is the corresponding position of reference circle, and this is SHM position. When it has angular displacement of 60 degree, a corresponding projection is here. So it has this where it would appear on SHM motion. When angular displacement is 90 degree, how we are measuring angle? We are measuring angle in this direction to be positive, starting from x-axis. When it is 90, the corresponding projection is here. So this is a reference circle, and this is SHM motion. When object moves, we can find the corresponding position. Corresponding this is a corresponding position. In all cases, you notice here, every case, this position, where it is going upwards. Here it is going upward, and this is momentary rest. Here also it was upward motion. What will happen after another 30 degree? When it travel from here another 30 degree, or from initial position 120 degree, the particle will come back here. So these two are identical position as for an SHM. On reference circle, there are two different positions. For SHM motion, these are two identical positions. One case it was going up, which is corresponding to this. When it is going down, it corresponds to phase angle of 120 degree. What do you understand here? When it was going up, the phase angle was 60 degree. When it is going away from the mean position, and when it's coming towards mean position, phase angle is 120 degree. So something like this happens, so corresponding like another 30 degree, this angle becomes 150 degree. So this is 30 degree and 150 degree. So phase angle of 30 degree and 150 degree is position is same, but direction of motion is opposite. So that's what we need to understand. And moment we see is a position of an object undergoing SHM motion, our mind should be able to find out what is the phase angle. And anything on the positive side, phase angle will be 0 to 180. And anything on the negative side, phase angle will be 180 to 360, or 0 to minus 180. So for each position, what we notice for each position, except for the extreme position, there are two phase angles possible depending on direction of motion. So every position there are, except for the extreme position, there's only one phase angle here. Everything like 60, 20, 30, 150, and this is 0, 180 degree. So every position, there are two different phase angles possible, because there are two different positions on the reference circle. If there are two positions in the reference circle, there are two angles possible. But which is the correct phase angle, that will depend on direction of motion. So they have to see, have to visualize which direction it is moving. We can find phase angle. Why phase angle important? Because from phase angle, we can find position, velocity, and acceleration. Okay, now we understand why it is relevant in case of a wave motion. Wave motion, we have discussed, wave motion is something wave moving on a string. So let's try and understand why. Let's take let's take this one point here. Let's take another point. This has certain spacing, and phase angle, did phase angle differ by 30 degree. Let's say this point is going downwards. If this particle is going downwards, its phase angle will be 180 degree. And this one is okay. If this also is going down, this phase will be 150 degree, and so on. So what we have done here, if we mark different particles, all particles are equally spaced, and phase angle also changes by 30 degree. So change in phase angle is equal for equal distance. These are the, we have marked certain position. How many particles we mark? We mark 6 particles. So there are 6 equally spaced points. All are having SHM. So this point is having SHM along this line. All are having SHM along vertical line. So all are depending on the position, they have a phase angle, and all phase angle differ by 30 from the previous one. So the phase lag of 30 degree. So this 180, 150, and so on and so forth. They're all lagging compared to this one. Now what will happen if they're undergoing SHM motion? With time, their phase will change. So if we take a time, after time, let's take after time t by 12 seconds. If all are undergoing SHM vertical line, their position on the vertical line will change. If we take another snapshot after t by 12, all angles will increase by 30 degree. So this point will come to a position where phase angle is 210 degree. And similarly, if I mark this where the first point will come, so this phase will become 210, this will become 180, this will become, which was 120, now becomes 150. So all points phase will change by, since all are having same angular frequency, all phase will change by equal. So this is how, if this 6 particles, the blue dot indicate their position at t is equal to 0. Red dot indicates their position at t by 12. After time, which is 1/12 of time period. In 1/12 of time period, phase angle will change by 30 degree. So we have taken 6 points. Had we taken multiple points here, all multiple points are undergoing SHM and vertical line. If there's taken several points, all blue, if we join all those blue points, this initial position would have looked like this, several particles connected like this. And if we take their position a little time later, it will become all red dots connected together. So it will appear as if the whole waveform has moved towards right. It will appear, has the particle moved towards right? No, the particle has not moved towards right. Particles are undergoing SHM motion in the vertical direction. But if all particles which are at equal distance, if the phase difference also is equal, they will, if so, their number of particles, they'll form a continuous series of particles. It will form a like a rope kind of thing, like a string. And in time t by 12, all will appear to have shifted towards right. This is what has shifted, not the particle. Its waveform has shifted. That's the point what we need to understand in case of wave motion. After t by 12, which will shift by 30 degree, phase difference will remain unchanged. So this also, the phase difference between two particles, if initial was 30 degree, later on also remain 30 degree, as long as all of have same omega. Okay, so we talk about 2 types of wave. One, mechanical wave. We have seen EM wave earlier. Mechanical wave. What is mechanical wave? It needs a medium, something like a string, and which has elastic property, initial property. And in this case, what is the constituent particles? So there has to have some medium particles, and medium particles oscillate. What kind of oscillation? If the traveling wave has a shape in form of a sine function, the particles also undergo SHM motion. So what happens here? This is something briefly discussed. If we create a disturbance at the source, if we create a jerk at the source, we'll find whatever disturbance we have created, it will keep traveling on a string. If this kind of bump will keep travel towards, it will keep travel at a particular speed. So disturbance at source travels to other points in the space. And further, the point is, it will take more time for disturbance to reach. Another similar way you can think of, suppose you create a sudden clicking sound, tuck karke sound if you make. So if you make a sound here, So if a person stands here, he will hear the sound. If this person at a distance d here, he will hear the sound only for a very brief period when the sound was created. He will see, suppose he hears a time t1. Another person which is at a distance of 2d, he will hear the same sound at a distance time equal to 2t1, twice as that. So here also what is happening, the disturbance which has been created here, in sound also exactly same it happens. Whatever nature of disturbance is created, whatever wave pulse is created here, it travels in space. And the time taken to reach a point, the farther the point is, more is the time taken for disturbance to reach a particular point. That is to travel to other points in the space. So time taken for a disturbance to reach a point in space will depend on the distance from the source. So there's a time lag. So what I'm saying, in case of string, see, in case of sound, it is different. Energy is dissipated. In case of string, whatever energy we give here, the energy remains within the rope only. It doesn't lose energy. So what happens in case of a string, whatever nature of motion we give at source, same nature of motion, all particles undergo same nature of motion with a time lag. So all particles on the string undergo same nature of motion with successive time delay. That's a wave. And as they receive this disturbances here, they receive energy also. So as we see, as the pulse is traveling, so we can say the pulse is traveling, we can say the displacement is traveling, we can say the waveform is traveling, we can also say energy is traveling, all are same. So in this case, in case of wave, the energy gets transferred from one point to other without the bulk motion of the medium particles. That also is a wave. It's a transfer of energy. And similar thing can happen in case of spring. We'll come to that later, which happens in case of sound wave. Just imagine there's a spring kind of thing, and spring at one end, if you give a jerk here, as you move the spring towards right, what will happen? Spacing between different uh, this is like a helical spring, the pitch will come down. So basically it will get compressed, and the compression also will travel along the length of the spring. So we'll come to spring later. What is the difference between the two? In this case, wave traveling in this direction, particle is traveling in the perpendicular direction. Particle motion is perpendicular to direction which the wave travels. This is transverse wave. In this case, the different particles here, different particles of the string also, motion of particle also in the same direction, wave motion also in the same direction. This is called longitudinal wave. Longitudinal will come later. Initial part will focus only on transverse wave, which happens on a string. So if we create only one jerk, it will create only one bump which will travel. But if we create SHM motion, if we this point it is connected to something like SHM source here. If we connect it to SHM source here, this part, it will undergo SHM motion in a line which is perpendicular to the rope. So slowly what will happen, whatever disturbance we are creating or whatever motion is being created here, which in this case is SHM, all particles will undergo same, they will mimic or they will copy the motion of the source with time lag. This will have lesser time lag, greater time lag, even greater time lag. So different parts of the string all will copy the motion which is happening at the source with time lag which is proportional to distance from the source. So if this motion is SHM, every particle on the string will go under SHM motion. So if a source motion is like this, a source motion is like this, is SHM equation. Every particle also will have SHM motion. And when you have SHM motion, there are three elements we use to define SHM motion. The three elements are amplitude of SHM motion, angular frequency, and phase constant. So in this case, what will happen? Different particles also, can we write a similar equation for another particle here on the string? We can write similar particle. What will happen here? The omega will be same because omega depends on the frequency of the source. So any SHM motion of any particle on the string, if we have continuous SHM here, everywhere omega will be same. If there's low loss of energy, A also will be same. Only thing which will change is the phase constant will keep on changing. Farther the particle is, greater is the time lag, and time lag is in terms of phase lag. So this is something, so you can think of it, another figure. And suppose this is source where it is connected. So by the time you have completed one oscillation, this string will look like this. This is how it will look like. So different points as we keep oscillating. This is after one oscillation. This is after little more. This is, and we see the disturbance which is being created here will keep traveling the string. Here the energy is confined. Here the disturbance is traveled only this much distance. Here the distance travel even further, even more distance. So what you're saying here, by the time when you look at this part of the string here, where is the which part of the string has energy and which part has no energy? This part has no energy here, and this entire part of the string has energy. So what has happened during this time interval, in time 2t, we see two wavelengths have been created, two waves have been created in time if we oscillate for, by the time we complete two oscillations here at the source. In the string also will have this kind of shape. If oscillation is SHM, string also will take a shape of a sine curve. So how much length? 2 lambda length will have energy. So energy which is being imparted at the source has traveled over a length, this much length, over a length 2 lambda in time 2t. So when the string start oscillating, it acquires energy, and where from the energy has come? Energy has come from the source. And we can see here, this basically the energy is traveling on the string. Early energy has reached up to this point. We can disturbance here, and it will keep moving like this. So can we write an equation if the disturbance is traveling in x direction? For a point, so if we take a point which is at a distance x, the time lag also, the greater the x is, greater is the lag, and the lag also will depend on, so minus kx. So what we need to do here, so greater the distance is, greater is the time delay or phase lag. It will lag. So basically the phase lag is proportional to distance from the source. So what is the equation? This will be the equation. And you understand what does yx mean? So if we have to find what is the position of any particle on the string having position x at time t. So the motion of any particle on the string will depend on two parameters, is position as well as time. And this expression, where from the kx has come? The kx has come because of time delay. So it will lag by how much? It will phase lag will be equal to kx. So that's the equation of a traveling wave. And this whole expression is called phase of the wave. And what is the term phi here? Phi is the phase at x is equal to 0 at time t is equal to 0. It's not a phase constant. We can say the phi is a phase constant at x is equal to 0, similar to SHM equation. So we notice here, compared to a single particle going under SHM, and this is multiple particles going SHM, continuous sequence of particles which are undergoing SHM, but with some time gap between adjacent particles. That's why the kx term has come. Let's understand how the wave motion, understand wave. So how do we understand wave motion? There's a particle motion. We understand in case of string, every particle in the string undergoes SHM motion in a direction perpendicular to length of the string. Let's say how does wave travel? Understand wave travel. So what we need to do, this is something, say at a particular instance, we take a snapshot. This is how the wave looks like. And we know this point is something special. We call it as a crest, and this point called is trough. So let's see what we do here to understand how the wave travels. Let's fix our attention to a particular crest here. It could be something else also, but I'm concentrating. Let's look at this point here. This is the crest here. So this is the crest, and if I look at time t by 8 later, at times say at time t by 4, after time t by 4, what I notice here, the shape of become like this. So where has my crest gone? If I keep observing from 0 to t by 4, I will see the crest which was here initially has moved to which point? See, actually the same thing we have drawn in different shape. So what has happened during time t by 4, the crest which was here has moved to which point? It has moved here. Another t by 4, this shape of wave will look like this, the crest would have moved here. So what is happening if I keep observing this wave, if I focus my attention only to one particular crest, this crest will appear to be moving towards right if the wave is traveling towards right. Okay, that's how and not only the crest, a similar way, if there are two people, person A looks at crest and he finds certain motion, certain nature of motion. Somebody looks at some other point also on the string, and particular point having a particular displacement. He'll also find, if both of them notice the motion, they'll find during equal time interval whatever displacement the crust had, other point also will have the same displacement, or you can say the point having zero displacement. So all will have, actually what would look like, it will look like not only the crust has shifted by lambda by 4 here, entire waveform has shifted by lambda by 4 here in time t by 4. The entire waveform appears to shift without the particle on the string actually moving in this direction. So this is apparent motion, that's what we call it a phase motion. What has shifted, we'll come to that phase again. So this is how it will appear to move. So if we take the snapshot at equal time interval t by 4, t by 4, t by 4, and that's what it will look like. And in time capital T, what we'll find, this is something, again, the waveform will look exactly as it was at the t is equal to 0. So after time t, the wave shapes exactly the same shape it had at time t is equal to 0. So the shape keeps repeating at time interval t, which is time period which should have happened. So what you notice here, how much distance the crust has moved in time t. The point which was here has moved to which point? It has moved here. How much distance? It has moved a length lambda. So, and this is true not only for crust, every point it is true. Any point on this wave shape, if I look at in time t, every point will move by distance lambda, which gives me an impression that wave shape moves at a constant speed. Okay, so if you observe any point on any other point on the waveform, it would have also moved the same distance. Okay. So, some of you can think of a frame of basically transformation of axis. Let's suppose this was the waveform. This is how it was at t at some time t is equal to 0. And if we just look at wave pulse, the wave pulse, it has moved here. This is how the wave moves. The shape of wave has not changed. Only thing is position has changed. So it is something liquid something like the transformation of axis. If I had a particular axis here, if I shift this axis from here by a distance equal to v into delta t, the function remains same. It is only, so it is basically, it is equivalent to, so if I use concept of transformation of axis, some of you may recall transformation of axis. I'm not going to do much, but here after time t, why? Because if it was original shape was fx, it becomes equal to fx minus x naught. X naught is the distance by which has shifted. And what is distance x naught? X naught is nothing but vt. In time t, it will shift by a distance. Whole wave shape has shifted by distance x naught. So this equation, if it was fx initially, it can be written as fx minus x naught. X naught is vt. So what we understand from here, we can generalize this one. Any wave, any traveling wave, the general form is, it's a function of x and t, is a linear function. Of what form? It is of form ax plus minus bt. That's the general form of any traveling wave. It cannot be x squared, that's the function. I will use that. Okay. Let's try and understand this equation. So what we need to know, suppose this is a shape which is given. So, and this equation which is given. So y is 4 mm sine. Let's try and understand what are things we can figure out from here. Can we find omega value from here? This equation, can we find omega value here? Okay. Yes, omega, we can spot what does the term A indicate. A indicate amplitude. This coefficient of t indicates value of omega. That much we know so far. Or we can say 100 pi is equal to 2 pi f, or frequency is 50. What else we can find out? Can we find out position of a string particle at x is equal to 1 by 12 meter at time t is equal to 0 second? Can we find out from this equation? So if the equation is given, can we find position of any particle? So can we find the displacement of any particle at a given time? All we need to do, substitute the corresponding value of x here and t here. It will give you the displacement of any particle at a given instance. Similar way, you can find t is equal to 0 if position of a string particle at x is equal to 1 by 6 meter at time t is equal to 1 by 300 second. How do we find it out? What is the position or displacement? I can position, we refer to y coordinate here. So how do you find the y coordinate? Pretty simple. It will simply substitute all the values. 4 mm sine of 100 pi in place of t, we'll write as 300, 1 by 300 minus 2 pi x is equal to 1 by 6. So this equation we can find out, okay, so we can find out displacement of any particular point on the string at any time by suitable substitution. Okay, let's understand. See, suppose I have substitute some constant value of time, which could be 1 second, 2 second, or in more general term, if a time t is taken as a constant, what does this equation represent? If I substitute time is equal to constant, what does this wave equation represent? If time t is equal to constant, if I substitute, it will be a relationship between y and x. It will represent the shape of wave at instance t naught. If I substitute time as a constant, I put time as a constant, it represents shape of the wave at that particular instance. And similarly, if I make not time, if I make x as a constant, if I choose x as a constant, means I have defined a particular point on the string. If x is taken a constant, this equation will represent the motion of a particular particle on the string. It will represent the motion of a fixed point on the string. And what would the motion be? It will be such a motion, y direction. Okay, let's try understand wave motion from here some more form. So let's say that this is a wave, this is a wave equation which is given. And you notice here I've written, it can be written in different form also. I've written omega t minus kx. Since I've written omega t minus kx, uh, if I plot the shape of this wave at time t is equal to 0, it will be a negative sine curve, negative sine function. And this will be the shape of wave at t is equal to 0. This is how the wave looks like at t is equal to 0. If this is a wave equation. Let's take a particular point P. And what is the point P here? Point P at X. And so basically we are taking yxt. What does yxt indicate? Yxt indicates y coordinate of point on the string having position X. At which time? At time is t. It gives a position. This is the equation. So this is the point P, xt we have identified. This is a point P here. Okay. Now, after some time, if the wave is moving towards right, this is how the shape of the wave will appear little time later. I think we have done it earlier also. This is how. So if this is time t is equal to 0, this is the shape of the wave a little time later. Let's understand here. And when we take this shape a little time later, what we think, if we are looking at point P here, we understand point P. What is special about point P? Point P is at a particular displacement or particular position on y coordinate. To us, to our senses, it will feel as if the point P has moved to P dash. This is P dash. What is P and P dash? What is P and P dash? Both have to have same y coordinate. So what is the distance P dash has moved? Can we find out? Let's try and understand here. Plus position of P dash at time t plus delta t. So this is the graph at time t. And this is, this is a wave shape at time t. This is a wave shape at time t plus delta t. So we are taking 2 point P and P dash. If P dash, see, suppose this is point P dash. And will the coordinate of P dash be same? No, the coordinate of P dash will not be same. If this distance is delta x, what will the coordinate of P dash? Y, x plus delta x. This is the position and this is the time, t plus delta t. This is the coordinate. If I substitute, and this will be equal to a sine, in place of t also is substituted t plus delta t, in plus x also is substituted x plus delta x. So this is the position of a point P dash, which is at distance x plus delta x from the origin and at time t plus delta t. If these two points have to have same y coordinate, what is the condition I apply if they have to have same y coordinate? If these two y coordinates are same, it means this phase angle has to be equal. So if P and P dash are at same y coordinate, this term and this term have to be equal. So if I equate, if y coordinate has to be same, if point P has moved to P dash, if I write this equation, the phase must be same. And when you simplify, this term omega t cancel out, kx cancels out. And what are we left with here? We are left with omega delta t is equal to k delta x. What is delta x by delta t? This is delta x. Delta x by dt indicates velocity of point P on the wave shape. Delta x by delta t indicates velocity of point P and it will be same for any point on the wave. And so delta x by delta t gives nothing but phase velocity or velocity of the waveform, and which is equal to delta x by delta t is omega by k. So how do we find wave velocity or phase velocity? Why we call this phase velocity? Because see, for point and p, if point p to move to p dash, the phase y coordinate has to be equal or phase has to be equal. Our phase has to be constant for waveform. Wave velocity, also called phase velocity, is equal to delta x by delta t, which is equal to omega by k. And how do we find wave velocity? We can find wave velocity by keeping this phase to be constant. If I take whatever phase is given, I have equated it to constant, and see if it has to remain constant, I take its derivative. If I take the derivative with reference to time, I get the wave velocity dx by dt. So rate of change in position of a constant phase. So d by dt of phase equate to 0, we get the wave velocity. Khyati?
Yes, sir.
Are you following this wave so far?
Yes, sir.
Karthike?
Yes, sir.
So when you see the wave equation, Karthike, are you following? Do you understand this wave equation? Why there's x term? No, what is the wave velocity? Have you followed wave velocity, Karthike?
Yes, sir.
Okay. Let's see. Okay. Now we come to something like we say wave velocity. What is particle velocity? Let's understand particle velocity. Okay. So again, we come to the point here. So this is the wave, traveling wave, moving wave. When is a transverse wave? How would the particle see? Actually, if I take this is a particular point on the string, and let's say this point, there's some point in the string we have marked with a blue color. Where would this blue color point move? Where would this blue color point on the string will move? This point on the string, which is the particle, will move from this position to this position. Its x coordinate will not change. So when the string is oscillating, every particle on the string, x coordinate will remain same. So this will be the apparent wave motion, and this is wave velocity, and this will be the particle velocity. And that's why I call it transverse wave. Particle velocity is always perpendicular to wave velocity. Any other particle, if I change here, so suppose this particle q here on the string. And if we continue oscillation, this point q, this particular phase has moved to point q dash. Has this particle moved? No, only this phase has moved is apparent motion. And this will give you wave velocity. But where has the particle actually moved? This particle x coordinate has remained same. Where is the x coordinate? Same x coordinate. Same x coordinate or same particle has moved from this position to this position. This is particle displacement and particle velocity. So we understand wave velocity is along the x-axis and particle velocity is in the perpendicular direction, and that's why it is called transverse wave. And so how do we define particle velocity? Its y coordinate is changing. So wave motion, x coordinate is changing. Particle motion, y coordinate is changing. So particle velocity will be equal to dy by dt. So dy by dt, and if I substitute any particular value of x and time, so if I write this expression, what this expression indicate? This indicates instantaneous velocity of a particle on the string at a position x naught at time t naught. So not only at particular instance of time, we have to also depends on also the position of the particle. So dy by dt is the particle velocity. And dx by dt, by equating the phase to a constant and taking dx by dt is the wave velocity. I hope this is one of the important point of transverse wave. I hope most of you have understood this point. Okay. So what particle velocity? This equation, can I find particle velocity? Yes, dy by dt. If I differentiate dy by dt, what is the expression we get here? This expression we get here. So this is a corresponding expression. And this is something you see we have already discussed earlier as well. All particles will undergo SHM motion. They'll follow the same property of SHM motion. So SHM motion, this is the particle velocity. What is the maximum particle velocity in this case? Maximum particle velocity when this term is equal to 1. And when this is 1, the maximum particle velocity is equal to a omega. So all particles on the string, they will not reach, but this particular particle, this is at a maximum particle velocity. This instantaneous velocity is 0. And this again maximum velocity. So different points will reach maximum velocity at different times, but maximum velocity of all particles during one time interval will be equal to omega a. That's maximum particle velocity. Where the particle has to be have to maximum velocity, property of SHM, velocity is maximum when the particle is at the mean position. So this particle is the maximum velocity. This is maximum velocity. This is maximum velocity. This particle at an instance is zero velocity, zero velocity, zero velocity. Okay. And what is particle acceleration? As the particle is moving, velocity is changing. Same SHM principle. So again, if we differentiate again, we get this expression, which is same equal to minus omega square a sine omega t minus kx. So what is maximum acceleration? Minus omega square a. When is the acceleration maximum? This point you have maximum acceleration. So when acceleration is maximum, and then phase equal to 90. This is sine function. So when is sine value maximum? When phase equal to this term angle is equal to either pi by 2 or 3 pi by 2. So this is maximum acceleration. Okay. Let's say 2 points are there. This 2 point, one is P and other is P dash. Both are oscillating. Both have same value of A. These two particles on the string, A values are same, omega is same. What is difference in between the two? If this has a phase, this has a phase constant of phi1, and this has a different phase constant. So they will have difference in phase. Okay, so let's understand how to find out phase difference between two particles which are at different positions. Where's point P? Point P is position is x coordinate is x1, and point P dash is x coordinate is x2. So we identified 2 points on the string which are at the position x1 and x2 on the string, and which is the wave. This is a wave equation. They are part of this wave. All particles in the string are part of this wave, which is traveling on the string. Now, what is phase of P here? If this equation, we can find out phase of P. We are interested in finding phase difference. So what we'll do, find the phase at a particular time. We find the phase of P. We'll find the phase of P dash. How do we find phase? We have to make appropriate substitution here. For point P, in place of x, since the position of P is x1, we substitute x1, and phase of P dash is omega t minus kx2. This is the phase of P at any variable time t, and this is phase of P dash any variable time t at same instance. Then this is the phase. So what is the difference in phase between the two? Phase difference is this is, we take this right as a phase difference. When we take the difference, what you notice, these two terms will cancel out, and this becomes equal to k times x2 minus x1. So what you notice here, t terms gets cancel out, and this term is independent of time. So phase difference at particular time, if I find some phase difference, any later time also phase difference will remain constant. It depends only on the distance between the 2 points and independent of time. And what is phase difference between 2 points? K into x2 minus x1. It can also be written as k into delta x. So any 2 points separated by equal distance, phase difference also will be same. So again, we come back to same equation. Phase difference is proportional to the distance. Okay, so phase difference, and this also important, and k will come to k term also again. We'll come find the k comes equal to 2 pi by lambda. So phase difference between 2 points separated by distance delta x is equal to k into delta x, and remains constant. It's not that we change, the phase difference will keep on changing. It remains constant. So let's look at some simple applications of the same. Our understanding gets better when we solve certain numericals. Let's look at this equation here. So first, what is the equation here? Moment you look at the equation, it represents the transverse wave. Yes, it is of what type of function? This is a function of ax plus minus bt form. And this is a function. Yes, this is of this form. So it is a traveling wave function, and x, y all are given here. Okay, we'll come to wavelength a little later. Well, can we find the velocity? Well, when we talk about wavelength, sorry, I think I didn't mention wavelength. I'll come to the wavelength also later. What is wavelength here? The k is equal to 2 pi by lambda. I think I mentioned last time. K term. What is k here? K is coefficient of x. The coefficient of x is called k, which is equal to 2 pi by lambda. So in this case, what are things we can find? If you have to find wave velocity, how do I find wave velocity? Wave velocity, even if I don't remember anything, I will wave velocity, the phase has to be constant. And this is a phase. The wave velocity, or called phase velocity. Let's write this one. Wave velocity is equal to what? Is also called phase velocity. What is phase velocity? How do you find phase velocity? Phase velocity means the phase has to remain constant. And what is phase here? Phase is constant. How is a constant phase moving? That's a wave motion. Motion of a constant phase is called wave motion. Phase is constant. Basically, phase is constant means what is the phase here? 200. Pi can be taken inside. Minus pi x by 25 is equal to constant. So what we do, we take is a derivative d by dt. Will give you wave velocity. D by dt 200 pi minus pi by 25. Dx by dt is v, wave velocity is equal to 0. So what is wave velocity equal to? Since everything is a distance in centimeter per second, so many centimeters per second, we divide by 100, we get into meter per second. So this is something I hope just keep is easy part here. And what is the omega here? 200 pi is omega. And what is wavelength? How do you find wavelength? Coefficient of x is equal to k value is equal to pi by 25. So pi by 25 is equal to 2 pi by lambda. So we get lambda also from here. Lambda is equal to 50 centimeter. Okay, let's do this question. This is also the wave. It's also again similar function. And x and y are in centimeter. Okay. Can we find acceleration of the particle located at x equal to 4 centimeter, t equal to 1 second? How do you find acceleration? See, suppose we had to find velocity, what you would have done? So suppose, let's do one, though the question asks only for acceleration. Suppose this equation given, if you have to find what velocity? Particle velocity. Which y direction particle is moving? Particle is moving in y direction. What is particle velocity? Particle velocity is equal to dy by dt. And once if we differentiate dy by dt, how much it comes to? It comes equal to 2 into coefficient of t is equal to 6 pi. And this becomes equal to cos 2 pi 3t minus x plus pi by 4. So any point, suppose you have to point velocity, similar way. Suppose you have to find a velocity at x is equal to 4 centimeter and t is equal to 1 second. What you'll do here, t is equal to 1 second. All I need to do is substitute the value of x here and t here. We can find velocity. Similar way, if you have to find particle acceleration, what is particle acceleration equal to? Particle acceleration is equal to second derivative of its motion, and that will be equal to minus a term into omega term square. Omega is equal to 6 pi square sine of 2 pi 3t minus x plus pi by 4. Now we substitute, we need acceleration at what time? We need d square by dt square is a function of at what time? At x is equal to 4 and t is equal to 1. We substitute those two values, minus 2 into you can find acceleration. Let's look at this question, a transfer wave. Again, it's a transfer wave. This question is about which are the thing it is asking. This equation, again, similar equation, t and x, and which direction the wave is traveling. It is traveling in positive x direction. When they're opposite, we can easily on differentiation, we find velocity becomes positive. So it is moving in positive x direction. The maximum particle velocity is equal to 4 times the wave velocity. So what we'll do here, let's find what is the maximum particle velocity. And then we find the wave velocity and substitute. So what is maximum particle velocity? Here all particles undergoing SHM motion, and maximum particle velocity SHM motion is equal to omega times a. So what is omega here? Omega is coefficient of t. So coefficient t also, this 2 pi is here. It is equal to 2 pi f, the term here, into x. Thus maximum particle velocity. And what is wave velocity? Particle velocity keeps on changing, but wave velocity is constant. What is wave velocity here? Either we can always keep in mind, I always find is take this derivative in your mind. Very simple. So wave velocity will be d by dt of, and if you want, you can memorize the formula also, x by lambda. So what this comes to, it comes equal to f minus 1 by lambda. Wave velocity is equal to 0, or wave velocity is equal to f lambda, which is a formula. We know that formula also. So now we substitute here. What is the condition? The maximum particle velocity is equal to 4 times the wave velocity. So this maximum particle velocity, we could have written as Vp max is equal to 4 times Vw. We just simply substitute here. So that's the condition. Or if it is equal 4 times any such question, we can easily solve. Hemant? Hemant?
Yes, sir.
Easy so far?
Yes, sir.
Okay. Next one. The frequency of a tuning fork. So this is something, okay. Velocity of sound in the air is 350. The distance to which sound travels by the time forks makes 125 vibrations. So this basically, this also pretty simple. Even without knowing much of wave also, you could have calculated how much distance will travel. Distance travel will be speed into time. Speed is given 350. See, it makes 500 oscillation in 1 second. So how much time it will take to make 125 oscillation? Time taken for 125 oscillation will be equal to, that will be speed. Sorry, that will be speed into that many meters it will travel. Okay, let's look at this one. This is not a traveling wave. What is given? They have given the two. These 2 points could be. Can these 2 points be on the same? Okay, this is the question. This question given here. Find the phase difference of velocity at particle 1 with respect to velocity of particle 2 at t is equal to 0. We have to find phase difference between velocity. So first thing, let's look at what is phase difference. How do you find phase difference? What is method of finding phase difference? To find phase difference, if I have two equations, one is like this, y1 is equal to a1 sine of omega t minus phi 1, and y2 is equal to sum to a2 into sine of omega dash t minus phi 2. See, at t is equal to 0, I can find phase difference. What is necessary to find phase difference? Both of them should be written in sine form. That's a typical way of finding phase difference. What we find here, one is given in the sine form, other is written in the chi-cos form. So first, to find phase difference, express both in same sine or cos function. Typically, we express in sine function. To express both in sine function, we could have done in cos function, but sine function is more common. So this is already in sine function. How do we convert? Basically, this is the y2 can be written as. But when we write in sine function, in this question it is not relevant, but both cases sine of omega t has to be same. Typically we take omega t, sine has to be taken as positive. So what we know here, so we use which principle, we use which trigonometric relationship, sine of pi by 2 plus theta is equal to cos theta. So we'll substitute sine pi by 2 plus pi t is this equation. Okay, so these are two equations, but we don't have to find phase difference between their position. We have to find phase difference between velocity. Actually, phase difference between positions and phase difference between velocity will be same, but we can do that also. So what is the velocity of particle 1? We could have found dy by dt. Okay, even before I do so, can we find delta phi between the two? What is phase difference between the two at t is equal to 0? So what I do is I find this equation at t is equal to 0. What is y1 at t is equal to 0? Y1 at t is equal to 0 is equal to 0.1 sine of pi by 3. And y2 is equal to what? 0.1 sine of pi by 2. So what is the phase difference between the two? Delta phi. That's the phase difference. Will the phase difference between velocity also be same as phase difference between position? In SHM property, whatever phase difference exists between position, same phase difference exists in velocity, and phase difference exists between acceleration. Not in the energy term, but as well phase difference are same. So I could have taken this also. Second way of finding would be I'll find the velocity of V1 and we can find velocity of V2 and again find the phase difference which will become same. Both will become cos function, but phase difference will come out same. You can verify this part also. But whenever we have to find phase difference in velocity, it will be same as phase difference between positions also.
Sir,
Yes.
so why do we take the modulus? Like, should we keep the answer positive all the time, or?
See, phase difference, I'll come to that part later. Why is phase difference relevant? Phase difference becomes, okay. Okay, I will not see. Just leave this question now for the time being. Okay. See, someday right now we don't know why it is so. We'll come to so we'll do some other parts also. We'll come back to this point later. Perhaps you'll understand better once we have some more application where we use the phase difference. In most cases, we use phase difference as modulus, and we will see later why we use modulus. The typical use of phase difference comes in a phenomena called interference. And interference, have you come across this word before?
Yes, sir.
Where have you come across this word before?
Wave optics.
Wave optics. But do you think it is relevant here also?
Yes.
Why? The wave optics also same thing. Wave optics also is a traveling wave. This also is a traveling wave. So what used to happen in case of interference there? You recall something about interference?
Yes, sir. The two waves have like different
So
phases.
if it's this is the two waves are reaching a common point, what will happen? So what this is something when they reach a common point. So if only one wave was there, it will have some oscillation, this particle, due to first wave. Due to second wave, it will have some oscillation. But when both are coming together, what kind of oscillation this particle will have? That's interference. The resultant oscillation will be phasor sum of oscillation of each wave, is it not? And then we calculate phasor sum. And why after calculating phasor sum, we can find out is amplitude and we can find out is the intensity also. We used to find intensity also. And when we calculate intensity, which is energy, energy depends on phase difference between two oscillations. It doesn't matter whether first one is leading or second one is leading. What really matters is the phase difference between the two. And that's where the phase difference becomes relevant here. So, and we had something like constructive interference and destructive interference. You recall what is constructive interference and destructive interference?
Yes, sir.
Okay. So reason I'm saying this is something, so when we calculate energy of resultant wave or intensity of resultant wave, it depends on phase difference, not in terms of which wave is leading, which is lagging. That's why we use most cases, we use that phase difference will be taken. Here they have given plus minus sign. So whenever plus minus sign are given, so just think of something like this. Okay, this question, sorry, this is suppose I give two phasors. One phasor is something like this, P1, other phasor is P. Sorry, this is a Y1 wave and this is Y2. Okay, So in this case, if you have to take phase difference, okay, phase difference will be equal to y1 minus y2. And if it was something like this, first particle is here and second particle is here. What will happen? Which one is leading? The second one is leading. It makes phase difference. If they ask what is the phase difference between the first particle and the second particle, it will come negative. Okay. So if so I didn't see that one, if the answer has negative term, we can also calculate in terms of sign. So we, in this case, would have calculated pi by 3 minus pi by 2. And if answer has a negative option also, we'll not take them all. But as we come see in the later part of the chapter, most cases, phenomena of interference only depends on magnitude of phase difference, not on the which one is leading or which one is lagging.
Yes.
Okay. This question, is this a wave? So what does it come to mind? Do you think this also is a wave? Is this a wave equation? So we are telling along this equation. So first of all, how do you check is a wave equation? Well, there are three conditions to check the wave condition. Third condition will not do today. Third condition will do tomorrow. Suppose the wave is wave. What are the things? First of all, it has to be form a continuous function. Now, basically, if it is wave equation, y cannot be indeterminate. Y cannot be equal to infinity anywhere. It has to be continuous, and y cannot be infinity. If y is infinity, it cannot be a wave. That's one condition. And what is the second condition for a wave? Second condition, it has to be always, function has to be what form? Function has to be a linear function of this nature. So is this of this nature? Yes, it is of this nature. It has been further squared, but this is something, this basic function, primary function is this. So is this a wave? Yes, this is equation of a wave. So, but it's not an SHM traveling wave. And this also is a wave function. Does it represent a wave? Yes, it is a form of this nature. And what is this form? It is this square of this, but it's still ax plus minus bt form. Is it continuous? Second thing, what we check, first we check this condition, second we check it continuous. Is this continuous? Yes, it is continuous. Nowhere it takes an infinite form. Denominator doesn't become 0. So it is continuous. It is of this form. It's a wave. So in this case, if it is a wave form, it is not a sine function. Can we find its shape of the wave? What will be the shape of the wave? The shape of the wave, how do we find the shape of the wave? We can find the shape of wave by particular value of time. If I put t is equal to 0 and plot y value for different value of x, I'll get the shape of the wave. How do we get shape of the wave? At a particular instance of time. So suppose I want to find out shape of wave at t is equal to 0. So for shape of the wave at t is equal to 0, I'll substitute t is equal to 0 in this equation. And when we plot y with respect to x, I get the shape of the wave. And what is the shape of wave will come here? What is the shape of the wave look like? What is the shape of the wave here? At what value of x at t is equal to 0? It will achieve, it will be, so this wave at t is equal to 0, y is equal to 4 by 2x square plus 2. So it will have a maximum value at x is equal to 0, and that will be equal to 2. So at x is equal to 0, it will have maximum value of 2. And from there, both sides, it is a, you notice it's a symmetric function. So it is, as x keeps increasing, the denominator keeps increasing, and y keeps decreasing. It will have something of this shape. So this is the kind of wave shape. And which direction is it moving? It is moving which direction? What is the velocity at which the wave shape is moving? This is the phase here, ax plus minus dbt form. To find, if you have to add one more question, what is the speed of the wave here? I can find speed of wave by differentiating ax plus minus bt function, which is 2x plus 40, which will come equal to 2 into velocity plus 4 is equal to 0, or wave velocity is equal to minus 2. So this wave will be traveling towards left with the speed of 2. If x is in meter and t in second, it will be 2 meters per second. It's traveling towards left. Okay, so I'll stop here. Think that's a basic equation of the wave, and we'll